Electrons to come off of the magnesium transferred is the key word that George said to the non-metal. Bell work up here, magnesium sulfide, and Hannah came up here and she gave us the... Who did?
Michaela.
Oh, Michaela did? Bless you, Michaela. So Michaela, nice job with the structure there. Now we need to put these together. As you can see on the bonding here, they're kind of showing you that they're having pluses there. That's kind of what they're looking for. But they're looking for the charge too. They're kind of looking for this and then this right here. That's what they're looking for on your sheet. So write that down. Now what we're going to do to take it to the next level, we're just going to put them together. So we use different markers for that. We'll use magnesium, maybe black. So we have and magnesium transfer. That was the key term we read about yesterday in the book. It talked about ionic compounds are transferring. So magnesium is transferring its electrons to sulfur. And when it does that, sulfur is going to behave like argon. So if you look in the periodic table, you're going to see argon, and it's mimicking this configuration. So it's going to be just as stable as argon is. And when magnesium transfers those electrons to sulfur, it's going to then behave like neon. Well, why don't you see the full electrons around magnesium like you see sulfur? Because they're lost. Moreover, sulfur, the nonmetal, is the one that's kind of in charge. It's the one that desires the electron. It's the reason why the reaction took place. So if you're wondering up here, you're like, Mr. Stonecker, why did that happen? Well, it happened because of the sulfur. That's why it's got the ring around it. Women typically wear the ring. Men don't as much because they can have their fingers ripped off. There was a shark. You seen the shark episode? Seen the shark episode on TV?
No.
The sharks. What's it called? Is it called the Sharks?
What? The show?
Shark Tank. Yeah, Shark Tank. They had a group of people came on there with rings that could come off of your finger in case you fall or if you're working around machinery. Because if your finger ring gets caught in machinery, it can rip it off. So once again, the ring is associated with the nonmetal due to its desire. You have to have a desire in life for things to occur, and the nonmetals are ones typically causing these reactions because of the desire. Start off here with our Lewis dot structures for oxygen. Then we're trying to get the goal to solve the puzzle is to get 8, because we're trying to get oxygen to behave like the noble gas neon. So the goal is for oxygen to behave like neon. In this situation, both of these oxygen atoms are behaving like neon because they have 8 around them. Now we call this process, Cody, what's this called?
This is called
No, ionic is transfer, covalent is share. Right, this is sharing.
Oh, covalent. I thought we were still talking about the ion.
We are. We're talking about this magnesium phosphide, but before we get there, I'm trying to help you understand what that structure is going to be, and we're looking at just oxygens and why they're going to bind together. These phosphides are going to bind together as well, but understanding this is a sharing happening is what the phosphides are going to do to make this ionic compound. So there's a little bit of both going on here. We haven't got to this section in the chapter, but we're kind of introducing it by looking at that. So this sharing is happening so they can behave like neon. If you put these double bonds here like that, that represents these electron pairs up here. Does everybody see that? Just a shorthand way. We're going a little bit faster. Any question on that? And you can see here that the electrons are going to move to where you have 3, so it can be 3 and 3. So these 3 here, because 3 and 2 is 5. Does everybody see that? So phosphorus is looking to form a triple bond and have your lone pair on the outside. Well, sometimes you have exceptions where you can have like 10 electrons to 12 electrons around the atom. We'll talk about more of that later. Structure for magnesium, right? Phosphorus, Garrett, you might want to write this down. Phosphorus has 10 electrons to work with, P2, in this situation. So we have 2, 4, 6, 8. So 2 of them are being, I guess you would say, taken or used in this bonding with magnesium. Because magnesium has 2 on the outside. And then you add 2 more and you get 8. So is it going to be your typical magnesium, I'm going to lose 2 electrons and behave like the other noble gas? Most likely not. This is one of those exceptions to the rules where you still have a single bond happening here, right? You don't typically show this with metals. Metals don't typically bond with themselves like you write like this, because metals don't form compounds. Like if you had magnesium and you had silver and you had gold, you're not going to see that because metals are basically alloys. They're mixtures, and they bond by transferring electrons, like you have a magnet. And in this situation, you're going to have a magnet because you have a mixture of metals. If you have just one metal type like iron, we don't typically show it like this. We show it like the handout showed you yesterday. This right here, where you have group 2 metals, electrons, 2 of them, moving through the metal and bonding with another metal. Does everybody see that? So this right here is telling you, this little dash right here is telling you that it's behaving a little bit differently because it's in an ionic compound. That is, magnesium is in an ionic compound. It's not acting as it would be in a metal. So there are always exceptions that happen, especially when you get things that are a little bit larger. So this, in a sense, is behaving like an ionic compound, which is what it is. And there's electrons that are moving around and making it most likely behave like magnesium is trying to behave like argon, because there's 8 electrons there to work with. Obviously phosphorus is lost 2. Once again, lattice energy cannot be directly measured. Lattice energy is a type of potential energy that can be defined in 2 ways. The lattice energy is energy required to break apart an ionic solid and convert its component atoms into gaseous ions. This definition causes the value for the lattice energy to always be positive, since this will always be an endothermic reaction. The other definition says lattice energy is the reverse process, meaning it is the energy released when gaseous ions bind to form an ionic solid. As implied in the definition, this process will always be exothermic. So you can really look at it 2 ways, either exothermic or endothermic. The textbook is defining the endothermic process. They're defining this is the amount of energy that is required to break apart these ionic compounds. So up here, we have a few ionic compounds that we just kind of dissolved in water this morning. And we're going to compare it to one covalent compound. We have ferric nitrate, calcium chloride, sodium chloride, and then we'll examine distilled water. This is plugged into an electrical outlet, and we can use conductivity to determine the lattice energy or the solubility. If it's more dissolved, then we can relate it to the lattice energy as far as it took more energy to dissolve this substance. Does that make sense? Like if you look at sodium chloride, its lattice energy is 769, and if you're going to compare it to, let's say, calcium chloride, the lattice energy is different. So let's take a look at distilled water first. You can see that there's no reaction with that at all. Does everybody see that? Now let's take a look at the ferric nitrate, right? So let's see what the ferric nitrate does. So the ferric nitrate is conducting electricity. That means this is very soluble. The ions are separated in here, and it's allowing electricity to travel across from one section of the water to the next. You can see in the beaker there that the electrodes are not touching. So I've got a beaker here that I'm going to use just to clean this. As you can see that they get dirty pretty easily. I just took some table salt. This would be your rock salt, and I put it in water. I did not heat the water. You can see that there's a little bit of water moving around. It's probably close to being super saturated.
Wouldn't that heat it though?
Well, it's basically room temperature water. If I put hot water in here, more of it would have dissolved because more energy would have been added to it. So you can see that it's not lighting up. So it's going to require a little bit of energy to break these bonds. Most of your, like if you have a pool that's salt water, they heated the water a little bit to increase the solubility to where it would, you know, be dissolved so it could kill the bacteria. Now this right here is sugar. We'll come back to that. And this one is, that's the sugar, and this one's the calcium chloride. Yeah, calcium chloride. So let's try that. So here's calcium chloride. No reaction there. And let's take a look at sugar. Let's clean that. Okay, the sugar not reacting very well either. So this is what we want you to remember about solubility. And typically in the lab, this is a very important thing to remember, because if you're making solutions out of ionic substances, you want to make sure you prepare them properly. Sometimes the procedure will call for heating the water. You're going to want to make sure you follow that procedure, because you're not going to get the reaction you're looking for if you don't. Certain solutions are required to be a specific molarity. So if you just added a little, let's say, deionized water, and then you added some salt in there, and it didn't dissolve properly, you're not going to get the required 0.1 molar solution because of the solubility. That's really the importance of this visual demonstration up here, is make sure you follow the procedure when you are doing a reaction. You're seeing magnesium and the sulfur. And once again, we learned yesterday that what's going to happen to the electron from magnesium? It's going to do what to the sulfur? Starts with a T. Raise your hand points. Transfer. Very good, Lou. So magnesium is going to transfer 2 of those electrons to the sulfur. The sulfur has 5 electrons there. It has 6 electrons. That was a 1 electron error there. Sorry about that. 2 negative was correct. Behaves like oxygen. So sulfur is going to look like this, where it is seeking to behave like the noble gas argon. So you'll notice that when sulfur gains those 2 electrons, it's going to behave like argon. And then magnesium is going to lose those 2, and it's going to behave like neon. I think it's AR. Excellent. So it's behaving like argon. Magnesium is behaving like neon. A direct measurement. Can you give me an example of a direct measurement? What? A teaspoon? Very good. Tablespoon?
Like those weird things at shoe stores.
Okay. Measuring your feet directly.
Yeah.
Foot measurement.
Like up close and personal.
Right. You can use a thermometer, Marcus. A thermometer would directly measure temperatures. Is everybody clear? Ransom, makes sense? Alright, so lattice energy, however, cannot be directly measured. So raise your hand, what is potential energy? Rain?
Energy that's stored.
Very good. So lattice energy is a type of potential energy that may be defined in two ways. So it's either exothermic or endothermic. The book is describing it as endothermic, and that it's the energy required to break apart the ionic solid.
The little ice cream stuff.
No, I have not.
You've seen like that before? Now, calcium chloride is something you're going to put on the road. If you go and you purchase it at the store, this would be something you sprinkle on your sidewalk. Calcium chloride. A lot of people use different de-icing methods when we have snowstorms. We just had one here about a week ago. They say the newest de-icing salt is magnesium chloride. Are our roads department using it? They might be. It wouldn't surprise me if they are. It will continue to melt snow and ice below negative 25 degrees Celsius. This salt releases about 40% less chloride into the environment than rock salt or calcium chloride. So that's really the issue. Calcium chloride is preferred on your, I guess you would say, concrete, because it's going to release less of the chlorine into the environment and onto your sidewalk and damage it. If you put rock salt on there, the chlorine will actually pit into the concrete, and that's not good. If you see pits in your concrete, you're going to be a little bit concerned about that. So it is less damaging to concrete surfaces of unknown or questionable quality. So keep that in mind to help you understand lattice energy and why it's important to follow directions when you're doing a lab. So first of all, if we take a look at distilled water, this is what distilled water looks like. So you don't see any reaction there at all, right? So now we're going to take a look at, this is right here, this is called ferric nitrate. Now ferric nitrate is an ionic compound. You have a metal and a non-metal, right? First thing you look for, you have a substance you don't know where it's of ionic or covalent. You see if it has a metal in it. This has a metal, so it's ionic. So if you put this in water, see that it is conducting electricity, right? It is a good conductor. Now, if you've ever been swimming in a saltwater pool, right? Salt water, you'll notice that, let me try to clean this a little bit. This is just distilled water, and the distilled water that I used initially had a little bit of the iron or ferric nitrate still present, so I'll need to clean that for next period. So let's take a look now at salt. Now this morning I just put some rock salt in water to help you understand a little bit about lattice energy. Just some salt in water. And you see that there's no current going through it at all. Now if I've had some salt water up here, the current would go through it. The reason why the current is not going through it is that I have not provided enough energy to dissolve the sodium chloride in this solution. So when you're doing a lab and it calls for, I don't know, 0.5 molar solution of sodium chloride, you need to make sure you follow the directions. It might say heat it and then let cool. So you have dissolved the right amount into the liquid. If you don't follow the directions, you're probably not going to get the desired solubility. You can see this sometimes if you're making like Kool-Aid. Now this right here is the sugar. So I just took some sugar. You can see the sugar in there didn't dissolve very well. You're going to see a similar thing with the sugar. No reactivity. This is calcium chloride. Same thing this morning. I just put a little bit of calcium chloride in the water, and you're not getting any reaction at all. So tomorrow I'll heat up the liquid and I'll show you the difference. We'll have a solution of sodium chloride. You're going to see that it heats up or lights up. Look on polyatomic ions as a review in the naming process. So go ahead, Rain.
Many ionic compounds contain polyatomic ions.
Okay, so the charge is going to be the same for the phosphide. It's going to be 2 minus. Now, on your test, on your quiz that is from last Friday, they had the H plus is the hydrogen ion. Now, H minus is the hydride. Because remember, the nonmetal is seeking to gain electrons. It's going to behave like that. So hydrogen can do a lot of different things. It can gain electrons. It can lose them. If it gains an electron, what's it behaving like? It's behaving like helium. Because remember, helium has 2 electrons. Okay, so the
salt has more. No, the salt has more or less than sugar.
Okay, so when we looked at lattice energy, there's 2 ways of examining. We'll talk about that in a minute. But the one in the book is looking at it from the endothermic process. That is, how much energy does it take to break the bonds. And I just mentioned to you that the state has this salt bath design thorough course task they want you to complete. Now, I'll probably give this to you maybe tomorrow, and we'll talk about it for a couple days, and I'll collect it from you. But the general idea is that these different salts, calcium, chloride, sodium chloride, potassium chloride, they require different amounts of energy to be associated with the solubility, just like you see in the book we talked about yesterday with the lattice energies. So these lattice energies are corresponding to the temperature. Temperature of the water would be the energy necessary to get the salts to dissolve. Does that make sense? It's what you're seeing here graphed. That's what they're showing you. A lot of people care about this because people make bath salts. That's the title of the thorough course task, salt bath design. So you wouldn't want to choose a salt that's not going to dissolve in the bath temperature you're looking for. So up here today, we have an example of this. Now this morning, I got some distilled water, and you can see that the distilled water has kind of reacted a little bit with one of my other chemicals, but it's not lighting up. I didn't clean that last period. I got busy answering an email. Sorry about that. But this right here is just your regular table salt, sodium chloride, that you have on your table. All I did was just take some room temperature water and put some salt in it. I did not heat the water to increase the solubility, to show you this concept of lattice energy. So you can see the salt at the bottom. Does everybody see that? So if I put this underneath or in this solution, it should light up. It's not lighting up because it's not been dissolved. Now this would be a problem if you have a saltwater pool. Now there's some things I could do. I could crush this, which would increase the surface area, which would cause it to dissolve a little bit quicker. It's in a crystal for a reason, for me to show you the significance of lattice energy. Now the next one we have is this right here. This is called calcium chloride. I'm going to walk around and show you what this looks like. Calcium chloride requires 2,254 kilojoules per mole of energy to dissolve. 769 kilojoules per mole to dissolve. So which one requires more energy to dissolve in water? Which one? Which one requires more energy to dissolve in water? The calcium chloride, or which one would I have to heat more? I can heat these and eventually the light will come on. Yes, I'll have to heat the calcium chloride more. Miracle. I'm trying to talk about salt and like snow. The sodium is going to require more heat to dissolve. Why is that important? Because if you look at chlorine, it damages. It uses magnesium chloride because it's less damaging to your asphalt or your concrete. Now it's going to cost you a little bit more, but the reason it's less damaging is because there's less chloride that gets released. This salt releases about 40% less chloride into the environment. Now when the chloride gets onto your concrete, specifically sodium chloride, because it requires less energy, when the sun hits it, when the sun comes out, hits the salt, it's going to warm up the concrete and it's going to dissolve the chloride, and it's going to start tearing up your concrete. You'll start to see pits in it. The concrete will pit. People don't like that. People don't like their concrete to crack and have pits.
What is the formula for the beryllium ion, the iodide ion, the nitride ion? Transition metals which are in groups 3 through 12 and metals in groups 13 and 14 are not included in table
7.12, and we're looking at aluminum compared to copper. You do have some aluminum wire that goes into your house. Some of your circuit breakers are aluminum. A lot of older houses had aluminum wire, but they're a fire hazard. So they stopped wiring houses with aluminum. But some of your higher voltage, they will still use aluminum wire. If you look at the melting point for aluminum compared to copper, which one do you think is a better conductor of electricity? Aluminum is 660 melting point. Copper is 1083 melting point. Which one would be a better conductor of electricity and why? Copper is better. Why? Yeah, it takes longer to heat up. A circuit breaker, if you're familiar with that, it will shut off the circuit once the wire starts to heat up. It'll tell you that, okay, there's a point where this is going to cause a fire because the wire is getting too hot. And if the melting point for aluminum is 660, it means it's going to heat up faster because it's 660, whereas copper is 1083. It's going to take a little bit more heat to get it to melt. Does that make sense?
Such as increased strength, some alloys.
It's not here. You got to a gym?
Home gym.
Or you got weights in your house?
I do.
Given this chemical formula. Recall that in ionic
So how you record this, you don't record it with the electrons there when you have a charge, and then you record them over here when you have a charge. That's the technical way they want you to see it. When you write it, like in the textbook. And that relates to what you're seeing over here. Yesterday we read in the book that ionic compounds do what, Maddie? No, it starts with a T. No, raise your hand. Transfer. Very good. I asked her initially. So they transfer. That's what's happening here. They're leaving the magnesium and going to the sulfur. Next question. Let's ask, I don't know. Let's ask Noah. The question is, when sulfur gains those 2 electrons, Emma, when sulfur gains those 2 electrons, what element is it behaving like? Raise your hand. Argon, right. So it's right here. You can see argon written right on the board there. Now, when magnesium loses 2 electrons, what's it behaving like? Neon. It's right here. See neon? That's the goal. Now the last question I have for you, Maddie. Last question. Why are the electrons only being shown around the sulfur? Why aren't they being shown around the magnesium? Trey? Why are the electrons only being... Both of these are behaving like noble gases. So both of them are nobility, are stable in this situation. Why are the electrons only being shown around the nonmetal? It's a very important thing to understand. It has to do with desire. The sulfur is the reason why the reaction takes place. Oxygen is the reason why a lot of reactions take place. The nonmetals are the reason why this happens. So that's why you're displaying that with the sulfur. You're giving it, I guess you'd say, precedence over the magnesium because it's responsible for why this took place. It desired the electrons, it took them. It says, look, this reaction only happened because of sulfur. Now, if magnesium wasn't there, obviously it would happen, but it forms this ionic bond because sulfur has the desire. It says, you're going to transfer those to me. Thank you very much.
More closely spaced ion charges. Because the electrostatic force of an electron and attraction between opposite charges increases as the distance between the charges decrease, smaller ions produce smaller.
Newest salt. And it says up here, it will continue to melt snow and ice well below negative 25 degrees Celsius. This salt releases about 40% less chloride. So I just mentioned to you that when you heat up, this is the table salt earlier, and we're noticing that the room is already heating up a little bit, and we're getting some increased solubility than we did earlier. So the question is, when you put the salt on the road or on the sidewalk, raise your hand if you know where the energy is coming from to increase the temperature.
Sunlight.
The sunlight. Yeah.
The points?
Yeah, I'll give you points for that. Now the point here is that the magnesium chloride is going to release 40% less chlorine. Will the calcium chloride release less chlorine? Yes. That's why you put the calcium chloride, these little dots, on your sidewalk. If you put sodium chloride on your sidewalk, it will dissolve your sidewalk. It'll start to cause it to pit because it releases almost all of the chloride, and the little chloride ions start reacting with your pavement. And that's not good. You don't want your sidewalk to dissolve. Why? They're expensive to replace. Yeah, you can repave your parking lot, and then if you do your sidewalks, it's a lot more money because you get into like concrete.
Are present, but still it has additional properties such as increased strength. Some alloys vary in properties depending on how they are manufactured. In the case of some metals,
Electrons to come off of the magnesium transferred is the key word that George said to the nonmetal.